Hi everyone, this is Kalyan Kumar here and welcome back once again to Chemistry Universe. In this video, which is the first video of the alcohol series, there'll be two videos in this. We will, as I said, we will start with alcohols. And this first video is about the introduction to alcohols and the preparation of alcohols. The second video that we'll be doing after this would be the physical and chemical properties of alcohols. And that would complete the entire alcohol series. Now, because I'm only going to make two videos on this, these videos are going to be a little longer. So if you're going to watch this, make sure that you watch this when you have sufficient time rather than watching it in breaks, because continuity is very, very important when you are studying a lesson. And needless to say, which I always say, is that make sure that you make notes while watching the video. Of course, when you go to chemistryuniverse.com, you can find the PDF there, but I would rather have you writing stuff, at least not, if not the text, at least the examples and the reaction mechanisms that will really help you a lot, because writing helps you focus. And if you want to pause in between anywhere, you can do that and complete your writing and then play the video back. And whenever I give you a question, make sure you pause the video, then you make the answer, make the product, make the solution on your own, and then only play the video back, because otherwise the purpose of giving the question gets defeated if you don't exercise your mind in doing that. So with that out of the way, let's start with alcohols, part 1, that is introduction and methods of preparation. All right, so here we go. The first one, first let's do the introduction. What are alcohols? So if this question were ever put to you, what would you say an alcohol is? I mean, we know what alcohols are as a functional group. It's a OH functional group. So if you're only going to say anything that contains OH, so what would you say water as? Water contains an OH, right? No, obviously I don't mean water. I mean a carbon containing OH. What do you think will happen to phenols? Don't they have an OH to a carbon? You say, no, I don't mean an aromatic ring. So as you keep looking at this, you will eventually reach a point where you will be inevitably able to make the definition as alcohols are the OH groups attached to an aliphatic carbon. So you have an aliphatic system on which you have a OH. Now remember that aliphatic system may at some place have an aromatic system as well. But as long as the OH is not directly connected to an aromatic system, only to an aliphatic system, it is an alcohol. So aliphatic hydroxy derivatives are called alcohols, while the aromatic hydroxy derivatives are called phenols. Now we can classify the alcohols in many different ways. One way is based on the number of OH groups. So we can have a monohydric alcohol, which contains only one OH. We can have a dihydric alcohol, something like this. Now, this particular one, generally, when you have vicinal OH, we call them as glycols. And this particular one is called the ethylene glycol. Then you have a trihydric alcohol, obviously containing 3 OH. Now, this particular one is called glycerol. Then you have the polyhydric ones, which have multiple OH groups. Remember, they don't have to be vicinal to each other. They can be at any distance. And if you have multiple OH groups, we call it polyhydric. But in this particular case, if I were to make this one, 6 carbon chain, each having an OH, then this particular one is called a sorbitol. But remember, as I said, it's not necessary that they have to be together. Now, another way of classifying these is by looking at the nature of the alpha carbon. So we can have a primary alcohol, the one that is attached, the OH is attached to a carbon which is primary. You have a secondary alcohol where the OH is attached to a carbon that is secondary. We have a tertiary alcohol where the OH is attached to a carbon that is tertiary. We even have what is called an allyl alcohol where the OH is attached to an allylic carbon. We have benzyl alcohols where the OH is attached to a benzylic carbon. All right. One more thing that we need to understand is, what do you think would be the bond angle, or what would be the bond angle of an alcohol compared to that of water? Now remember, water has a bond angle of close to 104.5, and that's because of the lone pair repulsion, which increases the lone pair bond pair repulsion also. And you find that the angle, which was supposed to be a tetrahedral angle, sort of shrinks. But what do you think will happen if in water I were to take one H out and put a CH3 in, methanol? What do you think will happen to the bond angle? Will it increase or decrease? Obviously, it's going to increase because of more space required for CH3, steric. So that would increase the bond angle. In fact, it increases the bond angle in methanol to close to 108.5. So this is methanol, and as I said, the angle is close to 108.5, whereas that of water is 104.5, and this is due to the steric repulsion of the methyl group. The bond angle in alcohol will increase. Now let's look at preparation of alcohols. Now there are many methods of preparing alcohols, and many of them we have done, so we will do them quickly. The first of which is oxidation of alkanes. Now remember, when we did alkanes, I gave you one method of preparing alkanes by the oxidation of KMnO4 that came under chemical oxidation. And where I said that whenever you have a tertiary carbon, you can remove its one H, the only one H that it has, and convert that into an OH by treating it with KMnO4. And that's what this one is about. So tertiary carbon undergoes oxidation in the presence of KMnO4 to tertiary alcohol, already discussed in alkanes, and this was the reaction that we talked about. And I had not even given the mechanism there because it's not required. Then comes hydration of alkenes. This is again something we have done in alkenes. It is just an alkene reacting with H3O plus. And as you remember, the general mechanism goes like this. This would go here. This would pick up the H plus, and you get a carbocation. And carbocations can always undergo rearrangement. And in this case, rearrangement is possible. So eventually the plus will land here, and it will give you this alcohol. So here you get a tertiary alcohol. Of course, you will get a bit of secondary and a very small bit of primary also. And already discussed in alkenes. Then we have Oxymercuration-Demercuration. Now, here we had again done this in alkenes. This was the Markovnikov product without rearrangement. So you use mercuric acetate in THF water, and then you reduce it with NaBH4, and you get the Markovnikov product without rearrangement. The next one again we have done, it's called the Hydroboration-Oxidation. And we have an alkene. This will give you a Markovnikov addition, but an anti-Markovnikov product. We use B2H6 in THF and then oxidize it with alkaline H2O2. And you got this. So remember, we have done all of this in alkenes. You can go back there and check out all the mechanisms. Everything is given there. So this is basically a repetition. Fifth one again we have done this in alkyl halides. Hydrolysis of alkyl halides. In fact, this is the most basic reaction of alkyl halides. That you take an alkyl halide and you treat it with aqueous KOH, the OH minus will replace the Cl, SN2 in this case, and you will get, or you can even use moist Ag2O. Remember, moist Ag2O gives AgOH, and ultimately you get OH minus, and that acts as a nucleophile, and you get alcohol. Now, we go to something new by reduction of carbonyl compounds. Now, carbonyl compounds, if you remember, we had done in organometallic, that an R minus, which will act as a nucleophile, will attack the carbonyl carbon, shift the pi bond to O, and eventually on hydration, the O will pick up the H and you get an alcohol. The difference here is we are going to make the nucleophile as H minus rather than R minus. So what happens when you have a carbonyl compound with an H minus? The H minus attacks the carbonyl carbon, the pi bond shifts to O, and on hydration, it will pick up the H. So you get again an alcohol. So carbonyl compounds can be reduced to alcohol, and these can be done in 5 different ways. Okay. And the first two are LAH and NaBH4, as they are very similar. But LAH, remember, uses a protic solvent, NaBH4 uses protic solvent. Now, LAH, as you can know, will break into this, and the AlH4 minus in turn breaks into H minus because aluminium is a metal. So H attached to it will be more electronegative. Now here you have an aldehyde and there is an H minus here. It will act as a nucleophile. What do you think it will do? It will attack the carbonyl carbon and the pi bond shifts to O, and temporarily you're going to get this. Obviously the cation associated with this will be there, Li plus. And then when you do the hydrolysis, you have to do the hydrolysis separately. When you do the hydrolysis, because LAH can't be used with a protic solvent. So once you treat it with LAH, once you get the product, you isolate the product and then react it with H2O and you'll get this. Now what you have to understand here is though, is that this H that you got, the H attached to carbon, came from LAH. Whereas this H that you got on O, you got it from water. So you have to understand where you get the 2H from. The reason this is important is because you may be asked questions like this. Suppose they give you a question like this: LiAlD4 followed by water. So where will you put the D and where will you put the H? So remember, the hydride comes from LAH, so which means the D will attach to carbon and the O gets an H from water, which will be an H rather than a D. So you will get this. Now NaBH4 does the same stuff. So NaBH4 will do the same stuff. Of course, it gives you a weaker hydride because it's not that strong reducing agent as LAH, but it is capable of reducing an aldehyde or ketone to an alcohol. So you get the same thing. Now the reason LAH is used in a protic solvent and in a protic solvent and NaBH in a protic solvent is because LAH gives H minus readily and therefore is a strong reducing agent. It cannot function in a protic solvent as it will pull off the proton from the solvent and form hydrogen gas, which is highly combustible. So it's difficult to do an experiment with. NaBH4 does not give hydride ion easily and needs the help of a protic solvent to release the hydride ion in the first place. So it's a weaker reducing agent. So LAH can reduce polar bonds. Now, another important thing is LAH can only reduce polar double bonds like the C double bond O or the C triple bond N. It cannot reduce a non-polar bond like a carbon double bond carbon or a carbon triple bond carbon. And this is true for both LAH and NaBH4. So both of these will reduce polar double bonds and not non-polar double bonds. So LAH can reduce polar bonds but not non-polar bonds of alkenes and alkynes. It is also true for NaBH4. So let's look at a couple of examples. Can you figure out the product? Pause the video. Figure out the product. And here's the solution. So obviously the carbon gets the H from the LAH, or the O gets the H from water, and you're going to get this. What do you think will happen with this one? Pause the video. Here's the solution. The carbon will get the H from LAH, O will get from water, but the carbon double bond carbon is not reduced. So what do you think will happen here? Pause the video, make the product, then play it back. Here is the solution. Same logic, H you get from NaBH4 on carbon and O gets the H from water. Double bond is not reduced and you get this. Alright, what do you think will happen if the double bond is conjugated? The earlier one, it was not conjugated. Pause the video. Make the product, then play it back. Remember, it doesn't really matter whether the double bond is conjugated or not. It's not going to reduce carbon double bond carbon. It is going to give you this product. And the same will be true even with NaBH4. It doesn't matter. So make the product, pause the video, make the product, play it back. And as I've already said, NaBH4 is not going to make any difference here. It is going to do this same thing. Look at this one. This is called cinnamaldehyde. Now, here there is a double bond that is conjugated with the carbonyl part. At the same time, the beta carbon has a benzene ring. So obviously, this must have some significance for me to talk about this, and it does. In this case, LAH will reduce the carbon double bond carbon as well, because this benzene ring is going to make this carbon extra nucleophilic, electrophilic. Instead of this carbon being more electrophilic, this becomes more electrophilic. And if you remember 1,4,1,2 addition we talked about, so you will find that LAH will reduce both. So if you were to react this with LAH and and water, you're going to get this. Remember, this only happens if there is a conjugated pi bond conjugated to the carbonyl part and the beta carbon has a phenyl group. But NaBH4 does not do that. It only reduces again the carbonyl part. So LAH reduces conjugated pi bonds if the beta carbon has a phenyl or an aryl group. NaBH4 does not reduce any conjugated pi bond. And moreover, LAH cannot even reduce the benzene ring. That is why the benzene ring is intact. This is called crotonaldehyde. Now, I want you to pause the video now and make the product and then play the video back. Obviously, here is the solution. Obviously, you can see that it does not have a benzene on the beta carbon. So carbon double bond carbon, despite being conjugated, is not going to get reduced. You will get this. The third type of reduction is called the Bouvet-Blanc reduction that uses sodium and ethanol. And the way this happens is very simple. Now, whenever you use a metal, remember, they always oxidize. And you have a carbonyl compound, it takes up one electron and forms a anion radical. Now, first this will take H plus from water, from alcohol. And then it will take one more electron, form a carbanion, which will again take an H from ethanol and form an alcohol. Now, the fourth reduction is called the Darson reduction using NaH. This mechanism is same as LAH because ultimately you get H minus here. And of course, the last of it is catalytic hydrogenation. So aldehydes and ketones will undergo catalytic hydrogenation just like alkenes and alkynes, and they will become alcohol. The next is from carboxylic acids and their derivatives. Now here we're going to spend some time. Now here remember, carboxylic acid and their derivatives, they have the C double bond O group in conjugation with a lone pair. The lone pair in acid comes from the O, OH. In acid chloride, it comes from the Cl. The ester, it comes from again the O. In amide, it comes from the N. So these are not that electrophilic carbons. So only LAH can reduce them, NaBH4 can't. So you have an acid treated with LAH H2O. So to make the product, you simply have to remove all bonds from carbon, and or rather you can say that, this acid can be written like this. Okay. Now this is only to help you make the product. Just remove this double bond O and put 2H. That is how you can make the product for an acid. And that's what you get here. Now, how this happens, the mechanism, again, it's not very important for you to learn, but I'm just showing you so that you can get some satisfaction of understanding how this happens. The H minus takes the OH, the H from acid, which is why we never use a protic solvent. But here, the reactant itself has a proton. So you will get the lithium salt of the acid. And this O minus will attack the Lewis acid AlH3. Because remember, LAH is given an H minus. It will form AlH3. And it forms a coordinate bond like this. Now from here, it takes out an H minus, attacks this, and this bond breaks. And you're going to get aldehyde. So first the acid becomes aldehyde on reduction. Let's not bother about what happens to Al. But LAH is in excess. So since LAH is still there, remember aldehyde, LAH, it will give you primary alcohol. The next is acid chloride. Same logic, remove the double bond O. In fact, remove the Cl also and just put primary alcohol. Again, you have H minus here. First, it will substitute. This is much more easier. You get aldehyde, and once you get an aldehyde, you will get a primary alcohol. Then you have an ester. And same logic applies here as well. You get primary alcohol. Now here what will happen is both will turn into primary alcohol. This part will turn into a primary alcohol. This part will turn into a primary alcohol. So you get RCH2OH and R prime CH2OH. Again, mechanism is not required as long as you can make the product. But the way it happens is that you have the ester, then you have an H minus, you have a nucleophilic substitution. You will get this and this. Remember this one, the lithium salt, we had already converted that into the alcohol in the case of a carboxylic acid. So that mechanism is same. And aldehyde, of course, will give you primary alcohol. Okay, so you have this ester. Now that was anhydride. This is ester. And in ester, it's pretty simple. You will get this as R CH2OH, whereas this will become R prime OH. So this is an ester. And mechanism is same. You will have nucleophilic substitution to give aldehyde and alkoxide. Now alkoxide, all that it needs is water, whereas this will reduce and both will become alcohols. Now another acid derivative is amide, but amide don't give alcohols, they give amines, primary amines. Amines don't give alcohols. So if you want to check out amides, amides will go like this and LAH and you get this. So again, there is a nucleophilic substitution there. You get this first. This is nucleophilic addition, in fact. And then ALH3, it forms this. You don't need to know all of this. It's not required. And you get iminium ion, which will be attacked by an H minus, and you'll get a primary amine. All right, now what we're going to do is we are going to use, we are going to see there are several reducing agents, and therefore we're going to check out what all these reducing agents do. So various functional groups and their products using different reducing agents. Now in this one, I'm using various types of reducing agents, not just LAH. I'm using various types. And I'm looking at multiple functional groups and telling you what happens to each of them. So that if you have more than one functional group of that category, and if you use one particular reducing agent, you should know which one reduces what and what, which one doesn't reduce. So you need to understand all of that. So I'm giving you that in one particular table. So I know it may look intimidating. And if you want to copy this, you can pause the video after this, all of the things come up on the screen, or else you can download the PDF at chemistryuniverse.com. So that's up to you. So this is the functional group that will be reducing. This is the product it will form, and these are the reducing agents: catalytic hydrogenation, LAH. Then we have DIBALH, that is called the diisobutyl aluminum hydride. Then you have NaBH4, and then you have tertiary butoxy aluminum hydride. So the first group that we have is aldehyde. Now aldehyde will always become alcohol when you reduce it, and all of them will do this. Aldehydes are the easiest to reduce. Then you have ketone. They will form obviously secondary alcohol. Again, all of them do this. Remember, these three actually are weak. These three are weak reducing agents, but they are capable of doing reduction to both aldehyde and ketone. But when it comes to acid, now acids, if at all you reduce them, they will either become aldehyde or they'll become alcohol, but they will eventually go to alcohol because even with aldehyde, the aldehyde will further get reduced. H2PT can't do. LAH does it. DIBALH is able to do it, but you can't do it with NaBH4 and last two. So obviously DIBALH is a little better than NaBH4 and the tributoxy aluminum hydride. If you look at acid chloride, well, since the carbon is more electrophilic in acid chloride than in acid, all of them can do it. If you take ester on the other hand, ester again a little bit resistant, they'll again form primary alcohol, but H2PT can do it. So can LAH. DIBALH not being that strong will only convert the ester into an aldehyde. But of course, the further aldehyde can be made into an alcohol, but you will have to use more equivalents of DIBALH, which we'll discuss shortly. But these two can't. Then you have the amide. Remember, amides will only become alcohols, amines. And H2PT can do it. LAH can do it. So can DIBALH. The last two can't. Then we have epoxide. Epoxides again become alcohols. The first three can do. And the last two can't. Then you have cyanide. Cyanides again become amines. H2PT can do, LAH can do, DIBALH can do. These two can't. And you have nitro. Nitro again becomes amine. H2PT can do, LAH can do, DIBALH can do. These two can't. And then eventually you have the carbon double bond carbon. Remember, it's a non-polar double bond. It will become an alkane. We know H2PT does it. We've done that. LAH can't. And none of the others can because they all are hydride donors. So they'll only do polar double bonds. Okay. And out of all of this, the reactivity order is also very important. The reactivity of hydride donors towards various reactants will be in this order. The acid chloride is better than aldehyde. Aldehyde is better than ketone. Ketone is better than imine. This is imine. Imine is better than ester. Ester is better than acid. Acid is better than amide. And cyanide comes at the end. Now, NaBH4 can reduce only the first four. That means NaBH4 can do acid chloride, can do aldehyde, can do ketone, can do imine, which you saw in that table. And you will find that, the others, ester, acid, amide, cyanide, it can't be done because it's a weak reducing agent. So let's do a couple of examples. Again, in each example, pause the video after I give you the reagents. Now pause the video, make the product, play the video back and check the product. Now remember, this part is ketone. It will become alcohol. Remember, this is an ester. LAH can reduce an ester. And what does LAH convert an ester to? If you have an ester like this, remember, this became RCH2OH and this part became R prime OH. So this is OR prime. So this will become OH and this will go and you get a CH2OH. So you will get something like this. Whereas if you were to do this with NaBH4, remember it doesn't do ester, it only does ketone. So you get this. And try this. Pause the video. And here is the solution. Remember, the LAH will reduce ketone to alcohol and nitro to amine. Whereas if you do the same thing with NaBH4, NaBH4 can't reduce nitro. Try this. Pause the video. Well, LAH can reduce both COH and ketone, does not reduce carbon double bond carbon. Try with this. Pause the video. Well, this can't reduce the acid or the double bond, only reduces ketone. And what do you think will happen with this? Well, if you remember, H2PT can reduce ketone, it can reduce carbon, double bond carbon, cannot reduce acid, and you get this. Now, regarding DIBALH and tributoxy aluminum hydride, there are a couple of things you need to know. Now, DIBALH and tertiary butoxy aluminum hydride have only one H to donate and are therefore weaker reducing agent, which is why in most of them you saw a cross. Now, if you were to use one equivalent of DIBALH in ester, it will become aldehyde, which I shown you in the table. But if you use more than one, two or three, then you will get, in fact, 3 and 4, you will get an alcohol. So if they were to say excess, nobody is going to tell you 3 or 4 equivalent. It's not important whether you remember this 3 or 4, but what you remember is one equivalent will convert into aldehyde and excess will convert into an alcohol. And this is for esters, remember. Whereas if you were to take acids, to convert them into aldehyde, you need 2 equivalent of DIBALH. And excess, well, we get alcohol. Now, lactones are basically cyclic esters. So, lactones with one equivalent of DIBALH form cyclic lactols, which is also called hemiacetal. And I'll show you this shortly in an example, which further converts to aldehyde and alcohol. That means what happens is when you use lactones, what are lactones? Lactones are cyclic esters, okay? Something like this. So what happens is this will form cyclic lactols. So what are cyclic lactols? Well, what happens is that you can just imagine that, let me just rewrite this. So what this basically does is the ring oxygen, you get OH here. The double bond O behaves like a ketone and forms an OH, but the ester part, the O, the ether type O remains. But this is called hemiacetal, part ether and part alcohol. And this will further convert, again, this will break and it will eventually become OH. So for that you need excess. In fact, you don't need excess. This itself will convert to that because this is unstable compound. And you'll see all of this when I explain the other part. And one more thing, alpha beta unsaturated esters with 2 equivalents of DIBALH get converted to allyl alcohols. Again, if you remember, you have 3 to 4 equivalents is what you need for normal esters. Whereas this requires 2 equivalent. One doesn't have to remember these numbers, but just as a matter of fact, I'm just giving you this data. So unsaturated esters, alpha beta, require 2 equivalent of DIBALH to convert them into allyl alcohols. The same time, nitriles will first become aldehydes and then become primary amines. So 1 equivalent of DIBALH will convert nitriles are cyanides. So 1 equivalent of DIBALH will convert them into aldehydes and more than 1 becomes primary amine. So let's check some of these out. So you have this and you have 1 equivalent of DIBALH. Now, obviously, it does not do anything with the double bond. It will only do this, and you don't, of course, need to know the mechanism here. There's no need to make this. Just make the final product, and that will be this. Basically, it is the nucleophilic attack, and you just have to make the final product. So they're going to give you 1 equivalent DIBALH followed by water. So what do you think will happen to this one? Well, pause the video. Well, as you can see, there is only one functional group capable of getting reduced, and that's a ketone, and DIBALH does reduce a ketone. Now, again, one might say that why did I put the OH on top and the H bottom? Because DIBALH itself is hindered. And as you can see, the top part is hindered due to this. So the hydride will always attack from the bottom, the side opposite to the hindered part. So the H is down. So the hydride attack occurs from the less hindered side of the carbonyl group. So DIBALH, now sometimes DIBALH is very extremely region selective or chemoselective. Reagent in the sense it tells to attack from the side which is less hindered. And chemoselective because it will only reduce certain specific functional group. So you have this one equivalent will give you this, and one more equivalent will give you the aldehyde, which requires one more equivalent to form alcohol. So if you remember, this is what we said. With acids, you need the two equivalent to convert that into aldehyde and more than two to convert that into a alcohol. So again, you just have to, if they give you one equivalent, just make aldehyde. They give you excess, make alcohol. So esters, remember, one equivalent forms aldehyde. And then more alcohol. Remember lactones I told you? First it will become hemiacetal. This is hemiacetal. The carbon is having OH as well as ether. But this is unstable. It will immediately form something like this. So you get, this product. Anyway, of course, if you have some more DIBALH, it will reduce the aldehyde part also. Remember nitrile? One equivalent I told you, it gives you an aldehyde. How does it give an aldehyde? Well, the DIBALH will convert this into a sort of an imine kind of a thing. And on hydrolysis of this, you will get aldehyde. Whereas if you use excess, if you use one equivalent and then followed by one more, or hydrolysis, you will find you will get amine. So if you have two equivalents of DIBALH, you will find it goes to amine. So you just have to remember the final products. Don't bother about the intermediates shown in between. All right. So here we go. Epoxides. So you have epoxide here. Now I use LiAlD4 followed by water. Now if you remember, this is going to be a typical SN2 type reaction. D- is going to attack. So where is it going to attack from? The D- is going to attack on the carbon that is less hindered because it is SN2. You're going to get this. What do you think will happen now? Pause the video. Make the product. I've already told you AlCl3 will form a coordinate bond with this. This becomes plus. Now it is, remember, SN2 with SN1 character. So the site of attack becomes SN1. The mode of attack, of course, is backward. It is SN2. So you get this. Then comes hydrolysis of esters. Now alkaline hydrolysis, pretty simple. You have an ester, you have base, and the ester will be converted into the acid, salt, and alcohol. This is the typical hydrolysis of esters. And you can have acidic hydrolysis also, acid catalyzed, but that would be in equilibrium. There it is important to understand where the O of OR goes. So if we were to do the hydrolysis of this, remember the O of the OR prime will always go with the alcohol. And you know the reaction is reversible, as well as it's called the pseudo-unimolecular reaction. Then we have some selective reductions. Now selective reductions, if you remember, I talked about regioselective, remember? The tertiary butoxyaluminum hydride, if you remember, reduces both aldehydes and ketones. If you remember, tertiary butoxyaluminum hydride, the last one in the table. But aldehydes, as I said, are more susceptible for reduction than ketones. So if you were to use only one equivalent, it will only reduce the aldehyde. You use more, it will reduce the ketone as well. But remember, if the ketone is highly hindered, only the aldehyde is going to be reduced irrespective of how much you put this. Because this itself is sterically hindered. So then comes reduction of primary amines. Now we have already done this when we did diazonium. Aliphatic diazoniums are never formed. When you take an aliphatic primary amine, if you put NaNO2 and HCl, it will always become ROH. But here R should not be either phenyl or methyl. Because if it is phenyl, the diazonium is stable enough to remain under 5 degrees Celsius. And if it is CH3NH2, now what happens is CH3NH2 is highly reactive towards SN2. So a part of it, let's say 50%, forms the diazonium. And even before water can attack, remember, there is, this becomes alcohol, let's say. So 50% becomes alcohol. 50% are yet to become alcohol. So even before water attacks, this being a better nucleophile, this will attack the carbon and release the nitrogen gas. So the major product you get with methylamine is always ether, dimethyl ether. So let's do a couple of examples. Pause the video. Pause the video now. So obviously you get ethanol. How about this one? Pause the video. Now here you might make a mistake. You might make a primary alcohol. Well, remember, the N2 plus is so good leaving group that it would leave and form a carbocation, which will rearrange. Despite being a primary carbocation, it will form, and the major product is this. The next preparation we've already done from Grignard's reagent when we did organometallic. So you have this, you have R double prime MgBr, H2O, and you get a tertiary alcohol if it is a ketone. And if you remember, in an ester, we use two equivalents because one would first convert that into a ketone, second would convert that into an alcohol, and you will get tertiary alcohol again. The next preparation is from oxygen. So RMGX, now you just have to remember the overall reaction, no need to remember the mechanism, even though I'm going to give you the mechanism. What you do is, you take 2 RMGX reacted with O2, you will first get 2 ROMGX. This, when treated with H+, will give you ROH. That's all you need to remember. 2 RMGX plus O2 gives you 2 RO minus, and that with acidification will give you alcohol. I'm just showing you how it is formed. So RMGX first breaks like this and forms R minus. The R minus will donate 1 electron to one of the oxygen atoms of oxygen, and the pi bond shifts to O. The left oxygen becomes a radical, R becomes a radical, and O becomes O minus, the right one. Now, obviously you have MgX, which is the cation, which will always be associated with O minus. Now what happens is another RMGX breaks to form R minus. Now remember this peroxide that was formed? Now here the O bond breaks in favor of O. You get RO minus, and there is an MgX already there, and this becomes O minus MgX. So what happens is this R minus meets this guy, this meets this guy. Both will yield the same product. Eventually you get ROMGX, both of which on acidification will give you alcohol. And remember, the R can be a phenyl group. So if you use this with oxygen, again you get phenol. Now you can make alcohols even from magnesium in alcohol. Only thing is here, you have a diol forming. So for example, if you have a ketone and if you use mercuric amalgam, magnesium amalgam and followed by water, you'll get this. So I want you to make the mechanism, to get the mechanism on your own. Pause the video now. And the hint will be, what do you think a metal generally does in all these mechanisms? Start from that point and see if you can get the mechanism right. Here is the solution. Metals always oxidize. That's what they do in our mechanisms. So you have 2 mole of ketone and you have 2 electrons, one for each. 1 electron attacks each of the carbonyl carbons and the pi bond shifts to O and you get 2 anion radicals. Now these anion radicals combine with each other at the carbon because they are radical, and you will get this. And that with water would give you this. Now another way of getting this is using B2H6. Now B2H6 followed by acidification is a wonderful method. If you remember, in alkenes, we talked about diborane followed by acidification. It gave an alkene became an alkane. And that was one of the ways of getting an alkane without catalytic hydrogenation. So what does this do? It converts it into an alcohol. Now B2H6 is a unique thing because it can reduce even carbon double bond carbon. So it reduces both polar and non-polar. And what it cannot reduce are the acid chlorides, the alkyl halides, the ethers, nitros, and oxime. Of course, there is no H here. So let's do a couple of examples. Acids. Well, acids become primary alcohol. Esters, they also become alcohols. Now, acids, remember, I told you on catalytic hydrogenation, they don't. But if you use Raney nickel and use very high temperature and pressure for a long time, it will become primary alcohol. Another way of doing catalytic hydrogenation on acid is if you use ruthenium carbon and then do hydrogenation, it will become alcohol. But remember, the traditional method of using nickel or platinum is not going to give you any reaction. And that is the end of methods of preparation. So I hope you were able to learn the methods of preparation of alcohols. Most of the mechanisms, most of the reactions we've already done. And that's what will happen as we progress towards more and more functional groups. Many of the reactions we would have already done. Remember, the preparation of one compound becomes a property of another and vice versa. So that way, but that's good because we do not have to waste so much time in doing all preparation and all properties because many of the reactions are repetitive. That also helps you in a way. I mean, it could be an advantage or a disadvantage. Advantage because you're able to recollect or you can just go back and forth and then realize, oh, I forgot this reaction, now I get it again. So it gives you an opportunity to relearn. At the same time, it keeps using reactions at the back. And if you haven't done them well or you don't remember, you will find them a bit of a problem. So it is both an advantage and a disadvantage. But I would try to believe that it is more of an advantage because it helps you revise stuff. So with that, I'll see you in the next video. Thank you for watching this.